This is the bonus question for the chapter 6 and the section frames and machine. So we have a load of 50 pounds on the hook. It's pound, 50 pounds on the hook. And the question is to find all the reaction force. So if we look at the different connections at B, we have a pin. So it means that we have a B ax and a B y. If we set our axes x and y horizontal and vertical, and so that's a B. At A, it's a full connection, it's a fixed connection. So it means that we have a x, because no translation on x. We have a y, no translation on y, and we have a moment, and that the reaction moment, that the moment inside the connection. It means that these connections stop the rotation. So if it stops the rotations, there is a moment. Okay, that's because it's a fixed connection. It's like attached to the ground, and it cannot translate or rotate at this place. Okay, so can we solve bx, by, ax, ay, and ma right away? No, because there's 5 unknown. So we will need to find the strategy there. Let's begin by a part of this structure where we have some information. The only part where we have an information is the pulley. So one, I will do the pulley E. So we will do the free body diagram of the pulley E. Okay. And the pulley E is attached to a rope. So it's attached to a pin in the middle, and there's a rope around. The rope, the tension in the rope there is the same than the weight, so it's 50, and it's horizontal. The horizontal tension in the rope, it's also 50 because it's a smooth pulley, frictionless pulley. There's no friction, so there's no loss of force between each side of the pulley. Okay, so a smooth frictionless pulley just change the direction of the tension, not the magnitude. And at the pin, so that's the pin in the middle, so there's 2 reaction force. I will call that EX and EY. Okay, that's a pin, so two reaction on X and on Y, 2 components of direction. And if we solve the equation on X, sum of the forces on X is equal to 0, we can say right away that EX is equal to 50 pounds to the right. And if we do sum of the forces on Y, it's equal to 0. We found that EY is equal to 50 pounds up. Okay, so that's what we learned with our first free body diagram. Now that we found the force in the pin and the tension in the rope, there's 2 options. We can use either ACD or ECB. No, that's not an E, it's a D. DCA or ECB. Okay, there's 2 members in this structure. If we look at DCA, we have 3 unknown there. We have the tension that we know, and we have some unknown at C. So it's necessary more than 3 unknowns, so we will not be able to solve. If you look at the beam ECB, we know the force in the pin. We have 2 unknown there, and at C, if we look at the connection at C, what we have, it's a normal contact. So we will have just 1 normal force, because we know the direction. We know that the direction of this force between the surface and the pin is normal to the surface, okay? Because it's a contact like this, like a roller contact, okay? So it's just a normal force. Now, inside the slot, it could be, let's just take another color so you can see better. It could be a contact in these directions or these directions. Okay, we don't know because the pin is stuck between both side of the third, okay, that we will find with our equations. So let's do second. Let's do the member B. Let's call that beam because there's a lot of forces on this one. Not only two, but okay, BCE. Okay, let's do the beam BCE. So first, okay, and there's a pin at B, a normal contact. Okay, so that's like this inside at that C, and there's a pin at E. Okay, the four that we know the pin connections. Okay, so the pin connection at E, the force on the pulley was to the right, so the force on the beam is to the left. So we have this EX, this one, that is 50 to the left, and this EY, so the force on the pulley was going up, so the force on the beam is going down, 50. Okay, so that's the two forces that we know. At B, we have BX. Oh, that's very big, sorry. Oops. Can I remove that? No? That's a BX. And the BY. And at C, we have a normal force. Is it going up or down? We don't know. Let's put it down, up. And I will call that NC. Okay, so that's a normal contact between the pin in the middle and the inside of the slot. Okay, if we look at this probability diagram, which formula we will use first? There is one unknown at C and two at B. So we will use first the sum of the moment about B is equal to 0. So we need all the distance from B. Okay, so let's look at that. Okay, so for the 50, what we need is this horizontal distance because this first 50 is vertical. So this is the 3 plus 3 at the 6 feet. Okay. For this 50, we need the vertical distance. The horizontal 50, we need the vertical distance. Remember that the distance should always be perpendicular to your force, to the line of action of your force. So this is the total of 4 plus 4, that's 8 feet. Now for NC, there's two options. We can project NC on X and Y, or we can find the perpendicular distance with NC, because NC is perpendicular to the beam, so the distance that we need is this distance there. Okay? Because NC is perpendicular there. So this is perpendicular like this. Okay. What is this distance? Let's look at this triangle there. This is 3 feet. This is 4 feet. So this distance BC is 5. It's our 3, 4, 5 triangles, magical triangles. Okay. So this distance there, it's 5. Okay, so let's write our equation. Sum of the moment about B. We have this 50 is going to rotate in the negative directions. So we have minus 50 times 6. This 50 there is going to rotate in the plus direction. So that's the horizontal 50, so plus 50 times 8. And NC is going to rotate in the plus direction. So plus NC times 5, it's equal to 0. Okay, so we have 5 times NC, that is equal to, I need to switch the sign. Okay, so 50 times 6 minus 50 times 8. And we found that NC, so this is 50 times 2 minus 50 times 2, 100 divided by 5. It's minus 20 pounds. Okay, so it means that our force is not going down, not going up, it's should going down to be plus in this direction. Let's square this NC that we found. Okay, so right now our NC, I will leave it like this on this property diagram. I don't change the sign, but I need to include this minus sign in my equation of force on X and force on Y. Okay, so let's find which one first? Anyway, that's the same. Bx, so sum of the force on X, it's equal to 0. Oh, right now, there's something very important there. How do we find the directions of this NC? Okay, let me do this. Let me explain that on the right. Oops. Okay. This is my 3, 4, 5 triangles, this direction there. And the question is, what is the direction of this line? Okay. What is the direction of this line? Okay. So if we draw the X and Y axis like this, so that's my X and that's my Y axis, okay? What I simply do is I take these triangles, okay, and I rotate 90 degrees. And I can rotate in this one, I can rotate it in this one, or I can rotate it in this one. Okay, so this is always 3, 4, and 5, 3, 4, and 5, and 3, 4, and 5. Okay, I have rotated my triangles 90 degrees, and this point is always between 4 and 5. This angle is always between 4 and 5, always between 4 and 5, between 4 and 5, because those angles there are the same, always the same, the three angles. Okay, so it means that my NC, okay, let's say that's the NC, okay, this X will be 4 divided by 5, and this Y will be 3 divided by 5. Okay, that's not true in this area. It's not the same, because this area, the angle there is the 90 minus this angle. Let's say it's alpha, it's the 90 minus alpha. Okay, so that's not the same. But if you skip one angle, okay, those blue angles should be the same, like blue angles, they should be the same. So that should be the angle between 4 and 5, the side 4 and the hypotenuse 5 all the time. Your hypotenuse should be parallel to your NC. Okay, and after that, the complement on X and on Y are the smaller sides. So the 4 divided by 5 for X and the 3 divided by 5 for Y. Okay. So now we can solve for some of the force on X. So we have Bx. Bx. For NC, this is minus because it's going down, and this side, the minus, is the side that is parallel to the 4. Okay, so the triangles, if I draw it there, that's the 3, 4, and 5. So that's minus NC times 4 divided by 5, and the 50 is minus 50. It's equal to 0. So we have Bx that is equal to NC times 4 divided by 5 plus 50. But be careful there. Our NC, remember, our NC is minus. So Bx is equal to minus 20 times 4 divided by 5 plus 50. So Bx is equal to minus 20 times 4 divided by 5 and plus 50. 34. 34 pounds to the right. Okay. And sum of the forces on Y, it's equal to 0. Give us the Y. So we have By going up, the NC plus, because it's the way I draw it is plus, okay, so plus NC, and that the Y side, so it's 3 divided by 5, and minus 50 for this forces there. So By is equal to minus NC times 3 divided by 5 plus 50. So by is equal to minus, NC is minus 20 times 3 divided by 5 and plus 50. So by is equal to plus 20 times 3 divided by 5. That is 12 plus 50. So it's 62 pounds. So we have Bx, we have our NC, and we have By. Okay, so that was the second free body diagram. Now, the last free body diagram. Let me do it on this side and I will go grab the other value. So let's draw number 3, the free body diagrams of the beam, the vertical beam DCA. So this is the beam. Let me just take the ruler. I can cheat. Okay. Easy, right? So that's a beam. Okay, so D, there's a tension at D, C, and A, the point A. So at the point A, we draw the 3 unknown, AX, AY, and MA. And again, MA, that's the reaction moment. At C, we know now, okay, at C. So at C, we have this NC. Remember that this NC should go down, okay, if we write it positive. So we should write it up to say that it's 20. Okay, so we should invert this NC at the end, so the NC should go down, but that the force of the pin on the beam BCE, so now the force of the pin on the beam DCA should be inverse. And for the directions, that's the same than what we found there. So that the 3, 4, 5 triangles. Okay, sorry, it's small. With the axis X and Y. At D, we have the tension the same than this one, 50. Okay. If we look at this free body diagram, what we do first will be the moment about A, because we have all our unknown at A, okay, and we will be able to solve for the moment A. So let me draw this point A there. We need the dimensions from A to C. This one, that is 4, and the dimension from D. Oh, let's take my ruler again. Oops. From D to A, that is 8 for the 50 tension force there. So let's do first the moment about, oops, let me remove that. Sum of the moment about A is equal to 0. So this one is rotating clockwise, a negative direction. So minus 50 times 8. So this one 50 times the distance 8, perpendicular distance. This 20 has 2 components. This one, let me do it. And this one, remember to keep all the arrows together. Okay, you cannot use this force. So this vertical force is going through the point A, so no moment. So the only force that creates a moment is the horizontal component, and it's rotating in the plus direction. Okay, so plus 20, the horizontal component is the component that is parallel to 4, so times 4 divided by 5, and times the distance 4. Okay, so this is the force on X, and this is the distance D. Okay, and plus MA. It's equal to 0. Okay, don't forget this moment. A moment, it's a free vector. We can draw it anywhere. So it's not because I draw it at A that it's 0. No, it's already a moment time a distance. Okay, we need to include that because that's what we need to find. So MA is equal to, so I switch those two on the other side. So 50 times 8 plus, my computer, rush it a bit, minus 20 times 16 divided by 5. So MA is equal to 400. So 50 times 8 minus 20 times 16 divided by 5. For 64, let me see if I write it correctly. Oh, I forgot the minus. 50 times 8 minus 20 times 16 divided by 5, 336. And it's pound feet. Okay, at the M. Okay, let's do the force on the Y. Sum of the forces on the Y, it's equal to 0. We have AY, and we have just this force, so plus the 20 times the vertical complement is the 3 divided by 5, it's equal to 0. So AY is equal to minus 12 pounds. So it means that AY is going down to be positive. And sum of the forces on X, it's equal to 0. So we have AX to the right minus 20 times this complement, vertical complement, so 4 divided by 5. I need to move this a little bit. 4 divided by 5 and plus 50, it's equal to 0. So AX, it's equal to plus 16 minus 50. So AX, it's equal to minus 34 pound. So we draw it to the right, so it means in fact it's going to the left. So to the left to be plus. Here we go. So we found the moment. It's plus, so it's the way we draw it. A Y that is going down with 12 pounds, and AX that is going to the left. I don't think we should. No, I don't have to put the pound at the end. Okay, so it means that if we come back on our free body diagram from the beginning, this one, okay, with what we found, let me try to have everything on one page. Okay, it's a bit bigger. We can replace those force. So if we come back on this free body diagram, what we found that Bx equal 34, By is equal to 62, Ax is going to the left 34, Ay is going down 12, and we have a moment A that is equal to 336. Okay, so let's open that a little bit bigger. That makes sense if we look overall like this. That makes sense because 34, where's my 34? That's this one. Okay, so that's this one. If we look at all the axe forces, 34 minus 34, 0. We have a static system. 62 minus the 12 is 50. 50 plus 50 is 0. We have something that is 0. And for this moment, it's a bit longer to check, but you can take the moment about B and check that 12 times 3, 36, plus 50 times 6, 300. Yes, the total is equal to 336. So it's at equilibrium, it's 0 too. So if we don't look anymore at the inside forces and we look overall in all of the structure, we should find again some of the forces on X equals 0, some of the forces on Y equals 0, and some of the moment equals 0. So it's a good way to check that all your free body diagram is correct. It's long. I know it's long. It's a long problem. It takes time, but doing step by step. one of the key is really the sign. Just be careful of your sign. And if you didn't find the right sign on the next two-body diagram, I recommend to draw your forces in the direction that is make it positive. That's a bit easier. So congratulations, you have finished the chapter 6. See you in the next chapter. Bye-bye.